Okay, going to take a moment this time to look at something a little bit different, and that is a lot of folks have been influenced by the work of Abramsky and Kuka and John Baez to view symmetric monoidal categories as um, um, process representations. And while I think that is certainly true um, for some notion of process, it doesn't capture a lot of processes. In particular, without a lot more work, you can't get mobility, and the reconfiguration of the communication topology is one of the essential aspects of processes, in my opinion. And so I wanted to show that you can get an interpretation of symmetric monoidal categories in the rho-calculus, and that it's fairly natural, but that the rho-calculus goes considerably farther. The same is true of the pi calculus and the ambient calculus and the blue calculus and a bunch of other symmetric process calculi. And this is just part of a general critique that the notion of process, that effectively category theory suffers from something that it suffers basically from a notion of static composition as opposed to dynamic composition. And that this has to be, if we want a real theory of process, we're going to have to provide that feature. And so there's something between category theory and the mobile process calculi that needs to arise. And this is part of a general critique that I have, is that a lot of times we don't have an understanding of expressiveness. So, once there was the Church-Turing hypothesis, people thought that, Turing machines were the be-all and end-all of expressiveness, but people working in the lambda calculus knew that that wasn't the case, that there was something special about the lambda calculus that made it more expressive than Turing machines for certain kinds of things. And in particular, those kinds of things have to do with program refactoring, right? So higher order functions give you this ability to do abstraction in a different way than Turing machines do. That trying to encode higher order capabilities in Turing machines is a lot of work. It's not trivial, and the code is very difficult to understand. Whereas in Lambda, Lambda is tailor-made for that sort of thing. But Lambda suffers from its inability to look at questions of complexity. And then when linear lambda came along many years later, right? So the lambda calculus was discovered in the 30s. Linear lambda calculus comes along in the 90s, effectively, right? So a good 60 years later. There are interesting questions about the interaction between higher order capabilities and complexity that show that discussion, that dialogue about expressiveness is useful and interesting, right? So Turing machines have something important to say, but they don't say everything. Lambda calculus has something important to say, but they don't say everything. The same is true when we get to concurrency, right? So Turing machines and lambda calculus are in fact sequential. You could write a coroutine processor in the lambda calculus, but that's a lot of code, and trying to navigate through all the code to understand what's going on in the concurrency is difficult, extremely difficult, and it's very easy to make mistakes. Providing syntactic support for concurrency is very important. I mean, it's essential if we want to be able to write correct programs. Not the least of which is that, you know, if you, whether you look at it from an automata point of view, or you look at it from writing, you look at concurrency from some kind of multiplexing or scheduling or co-routining kind of implementation.
Greg, do you have anyone in the waiting room?
Let me see. I didn't get any notifications. Right. So the point I'm trying to make is that no matter which way you go in terms of implementing concurrency in these other formalisms, the ability to statically analyze those formalisms is hampered by the complexity of the representations. So you get exponential blow up in either approach that I identified. And so it's not just that it's hard to reason about, it's that you become swamped with implementation complexity. So it is a real expressiveness characteristic when you move from something like lambda to something like pi, where you add the parallel composition. And then the same is true of mobility. So what happens with mobility is that it is possible to build an extensible switchboard. So you can provide a notion of a switchboard and some kind of entity that is switching amongst channels to provide this, just like an operator in an old style telecommunications network who is intercepting calls and providing the switching capability. So this sort of thing is you can understand it conceptually, and you can implement it, and you can make it extensible. But the reality is that the complexity of that makes it very difficult. And anyone who's had to do patch bays for a synthesizer or a mixing board, an old style mixing board or effects unit, understands what I'm talking about. The complexity becomes overwhelming beyond a certain number of communicating components. So it's the same sort of thing. The mobility and the right syntactic abstractions for mobility informs our understanding of the sorts of formalisms we need to support them. So the dialogue between different formalisms is important in the same way that category theory gives rise to interesting and useful insights. So Ionata is an example of an interesting and useful insight. Natural transformations and for that matter, infinity categories. These are all interesting and useful insights. However, uh, uh, um, they, so I don't think that we would have discovered the Unay dilemma if we had restricted our attention to the mobile process calculi. On the other hand, the mobile process calculi do something that's important that category theory doesn't do well, and that is this mobility. And so the moral of the story is just that the dialogue between different formalisms is important, and that there isn't one unifying formalism that's going to capture everything about how we reason formally about the world, and that it's good to have different formalisms and to look at how they compare and contrast, and to translate from one to the other, because that's the source of our learning, and really the strength of our math and science is this dialogue, as opposed to any one formalism dominating over everything else. So with that little preamble, I'll just give people a rough idea of what I'm talking about with respect to the mobile process calculi and symmetric monoidal stuff. So go here.
Greg, can I just ask you about what then in that context have a meaning of Turing complete, or like a universal computation, capable?
Yeah, so I think that that's actually an important question that really hasn't been given the right sort of attention. So in particular, it is not, in my mind, satisfying to use Turing machines as a yardstick for all models of computation. In particular, there isn't a theorem. The notion of Turing complete is only a hypothesis, right? So the hypothesis is that all models of computation that are, of a certain sophistication or a certain utility are ultimately interpretable either as lambda calculus or Turing machines. But I think that's sort of not even mathematically satisfying, right? What we would like is we'd like a property that we can check of a model of computation in itself without reference to anything else. And if the model has this ability, then it will automatically be what we call Turing complete, at least Turing complete. It might be stronger than Turing machines, but it will be at least Turing complete. And so, I think that this has to do with self-encoding. So, for example, in category theory, categories which are self-enriched. So, for example, Cartesian closed categories are self-enriched, right? So the Hom sets are again those kinds of categories. And so self-enrichment is a better way to talk about this property that can be that is normally recognized as either functionally complete or Turing complete. So I think there's actually rich area right there. And the difficulty is we don't know how to talk about all models. We don't have a formalism which allows us to talk about all models of computation. Right? There's so many of them. right? And there's such variety in the different, like in particular, it is very difficult to have a framework that spans, some kind of analytic framework where we can answer questions mathematically that spans, classical and quantum computation, just as one challenge for attempting to formalize that idea. But it's an important question. I don't think it's trivial. I think it bears some further investigation. All right. So the theory of symmetric monoidal categories is really the theory of boxes and wires. So you've got a box that has M inputs and N outputs. Some people draw them the other way around so that these are the inputs and those are the outputs. It doesn't really matter. And then there's some operations that you can do. You can compose boxes, right? So if the number of outputs matches the number of inputs, then you can wire up the outputs directly. You could, of course, do a partial wiring. So you have several boxes on top, and the boxes wire. So all of the outputs of one box go to some of the inputs to another box, and then all of the outputs of another box go to some of the inputs. Or it can go the other way. So some of the outputs can go to one box and some of the outputs can go to another box, right? So, but there's this idea of composition. And so hopefully that's making sense. So just to be super clear, I'll grab one of these. Get rid of the interpretations for a moment. So I can have, actually, let me just do a, so I haven't really said how many there are of these, but we could imagine that all of these get wired into some of these, right? So there's more of these than there are of these or these. In fact, we could say that if this is N1 and this is N2, then this is N1 plus N2, right? So we could wire all of these into here and all of these into here. And likewise, we can go the other way around, right? So if we could imagine that there are M1 inputs and M2 inputs, and there are M1 plus M2 outputs here, then we can wire M1 of these into here and M2 of these into here, right? And the only discipline that we have to respect is that we don't get to fork an output without paying for it somehow. So I can't take two wires from from the same port. So a wire from here and a wire from here to here and a wire from here to here, let's say. So that's what makes the thing monoidal as opposed to Cartesian, is that I have to pay for that copying in some way. So copying isn't free. So hopefully that makes sense. And then, so that's the operation of composition in sequential composition. And then there's an operation of parallel composition in which I just lay the boxes side by side, right? So this is parallel composition. I just put them side by side. So they're doing their thing independently of each other. Does that make sense? So do people kind of get, yeah. And then identities are just, straight through wires, right? So if I have just a box that's really just a pass through or a straight through wire, then whatever comes in before will just pass through. And so it's the same as if I just had this box. And if I put a straight through wire on the other side, whatever comes out will come out on the other side. So clearly it has identities, and we can, at least initially, use the count of the ports as our notion of types. Right? So that's that gives you a sense in which this is a category, and you can visually see that it is associative, and in fact, it's associative both. It's associative both sequentially, which is necessary to build the category, but it's also associative side by side. So hopefully all of that is clear, right? So boxes and wires gives you symmetric monoidal category, and in fact, these kinds of categories are in some sense paradigmatic. So you can think of them as providing a kind of representation for a goodly number of symmetric monoidal categories. You had a question?
I'm thinking how this parallel composition is represented in the category theory.
It's the tensor product. It's the monoidal product.
And the order is not important.
It can be important when it's a symmetric monoidal category. The order is not important. So if you just have a monoidal category, then the order is important. But when it's a symmetric monoidal, then you can swap these two. You have a symmetry which allows you to basically take all of these and run them over here, and take all of these and run them over here. That's your symmetry.
Mm-hmm. I mean, we are still keeping the same ports connected to the same side, right?
Yeah.
Okay.
Yeah. Okay. So then the idea is that we'd like to give an interpretation of the box in the rho-calculus. And I think it's very clear, right? If these are our inputs, right, then we want to label these, say, x1 through xm. So that's x1 through xm. And then we're going to pick up whatever signal comes in on that wire, and we're going to do something with it. And it is possible that we want to do some joins. And so we have to be a little bit careful about that. So we'll talk about how to be careful. And then eventually, if this is, there's n of these, then we think of these as Z1 through Zn ports. So really what we're saying is there's some context to which we can hand a process of this shape, so M of these processes, these are all guarded comprehensions, right? 4 comprehensions. And these are all the outputs. So there's some context that we can give these to that will utilize the X's and the Y's and the Z's to set up whatever logic is inside this box. So therefore it's clear, how to do the wires, right? So a wire that wires this to this it just, picks up on the Z's and passes them to the X's, right? And then goes back to being a wire. right? So in this case, right, we're picking up on Z11, the V11, and we're making sure that it's available to the X21. So this is 21, 22, 23, and so on. And so whatever showed up out of here shows up in here, and so on for all the different wires. All right, so that gives us composition. And we know how to do tensor, right? The symmetric thing, right? That would just be whatever this is in parallel composition with whatever that is. So clearly, with the same level of syntactic simplicity, we can do everything that the symmetric monoidal categories can do. But we can do things that the symmetric monoidal categories can't do, which is to cons up a fresh port syntactically and make it available to another box, right? So just like we had in this example here, right? So here's an example where the topology changes, the communication topology changes, and we can see how simple the syntax is and how easy it is to follow. So we've talked about this a couple of sessions now. So there's a clear argument that the syntactic capabilities of the symmetric monoidal categories are pretty much on par reflected, pun intended, on par reflected in the mobile process calculi. But the mobile process calculi give us something else that the symmetric monoidal categories do not give us. Now, just to generate some interest in the next Casper, what I'm going to do, and part of the reason for this discussion is symmetric monoidal categories end up being a relatively good framework for talking about quantum mechanics axiomatically. One of the most important steps that we need to add to symmetric monoidal categories in order to make them suitable for modeling quantum information and quantum computation is to add cups and caps. So you add wires which turn outputs into inputs, and wires that turn inputs into outputs. Sorry, did I get that wrong? I got that wrong, but you know what I mean. So if the picture is something like this. Let me. All right, so, oops, hello. Okay. All right, so if this is an input, right? So we're wiring an input, which is at the top. So the input becomes an output. And then the other one is this one. So we take an output and turn it into an input. And so there are some equations that we want to satisfy. Like if I do this, that is just a wire, right? And if I did it on the other side, it's also just a wire. And so there's a notion of yeah. So you want something like you can straighten it out, right? You can straighten this out, and it becomes a vertical wire. So that thing becomes one of these things. So that thing is equal to that thing.
What does it mean when output becomes input? I'm trying to somehow just connecting the ports, or
so I can take this thing and I can plug it here, and so it becomes a port up at the top.
So it's some kind of loop.
So yeah, so your intuitions about looping and tracing, those are all looping, recursion, iteration, that they all play a role here. Yeah,
I'm thinking in terms of rho. When if we have consume, how can this consume becomes produce?
They're all great questions, and we will talk about them next time. I'm already 5 minutes over. So I'm glad that your appetite is whetted. So yes, we'll give an interpretation of cup and cap in terms of rho, right? Because what you have to have, you're exactly right, that you have to have a kind of reversibility that isn't present in rho, right? So if you can turn outputs to inputs, then you have to have some kind of reversibility. And that's what makes it. So when you have cup and capped and you have this reversibility, and reversibility is a kind of physical representation or physical intuition behind unitarity. So you're looking for unitary. So things that are not measurements are unitary, right? So those are the kinds of transforms that quantum computation looks at, is these effectively reversible stuff until you measure. Everything's reversible until you measure. Yeah, so we have to, and so the trick, so if you go back to that paper that I wrote for how to do gas using rho, the same trick is there, which is this continuation saturation, right? So you can turn every rho-calculus process into one that does, before it takes any input-output step, it is asking for the continuation. So it takes as a parameter what to do next after input and output, right? So with that, you can record all inputs and outputs, and therefore run them backwards.
Yes.
Right. So we're using the same trick to do gas, right? Which is, you recognize this is an input, so you charge gas for it. You recognize this is an output, so you charge gas for it. So the other thing we could do, as opposed to charging gas for it, is to simply record what we've done. And so we can run things backwards. And that, by the way, is the same mechanism to use for debugging rho. It's exactly the same mechanism. You can use the apparatus that we have for cost accounting to create a debugger. That's why this stuff is important for our chain, is thinking through these things gives us insight into the practical considerations for building a realistic system. Debuggers need to go backwards and forwards in time. And that reversibility is key to unitarity. Isn't that amazing? Like you'd never expect that thinking about quantum computation would lead you to practical considerations for realistic deployments of our chain. But in fact, it very much does. And on that note, thank you very much for your time and attention. And I'll see you guys next week. And I'll see many of you in the Dev Stand Up in just a few minutes. Ciao, ciao.
Thanks, Greg.
Bye-bye.